Oh, that's fair. That's fair. Do you guys want to start with some questions from homeworks?
Yes.
Let's do that. Giselle, you want to start?
Who's number 17?
From
5.5.
I'm sorry, can you 5.5 number 17?
17, yeah.
Okay. I thought I remembered, but by the time I got to section 5.5, I wasn't sure anymore. Okay. So what did you think for your choice of U here?
Well, maybe 1 minus
Yeah. And I guess let's call this, I'm going to call this V so there's not any variable confusion going on here, since the problem has U's in it. So the derivative of V is just negative e to the u. So we'll make negative dv equal e to the du, or e to the u times du. So we have then 1 over v squared times negative dv. Or we'll think about that as negative the integral of u to the negative 2 dv. But now it's just a, power property antiderivative.
a lot easier when I made it in my head.
And that should do it. Sometimes it's one of those that like you just like you have the right idea, but you had to kind of see it through to the end. But sometimes it didn't look like it's going to be nice, and it turns out, oh, look, it all just fit together, and it wasn't so bad. Who's next? Elena. Same section? Okay. Okay. Okay, so what was your choice of U here? Yeah, definitely would be. And you like that one because you see it's nested inside of that fourth power, right? Okay, so our derivative then is going to be 3x squared plus 3. And I noticed that I don't have a 3x squared plus 3, but I have an x squared plus 1. So if I divide the 3 over, I'll have what I need then, right? So we have now u to the fourth times du over 3. I'll just pull that 1/3 out front. And again, now this is just a normal power property antiderivative. So we have 1/3 still u to the 5 over 5 plus c. Oh, I forgot to put the thingy back in up here, right? Sorry. Yeep. I'll just do that. Does that feel okay, Elena? Again, looked a little dicey at the start, but when you actually take that antiderivative, you see that like, oh, yep, everything is going to work out. It's going to all like click together pretty nicely. As long as you're pretty good about choosing your u, and you can competently do a derivative, usually things work out pretty nicely. Now, there certainly were some tricky ones that required like additional substitutions, but like this was not one. Who else? Rita? 74. Yeah, that's pretty deep down in there, huh? Oh, it has words on it too. It's always scary. All right, let's see here. It says verify that f of x equals sine of the cube root of x is an odd function, and then use that fact to show that this integral is somewhere between 0 and 1. Okay? So let's do the odd part first. To show odd, we need to show that f of negative x is equal to negative f of x, right? Okay. That's what we need to show. So that's going to be sine of the cube root of negative x, right? So when I take the cube root of a negative, like the cube root of negative 1 is going to be, it's going to be negative 1, right? Because negative 1 times negative 1 times negative 1 is negative 1. Or if I take the cube root of negative 2, that should be negative of the cube root of 2, because I can do that, right? So I can do that, right? Everybody feels okay with allowing that? Now, the second thing is that sine of a negative, sine I know is an odd function, right? Like sine of, negative 45 is negative sine of 45. So that I can pull out, and that is my negative f of x. So there's our odd. And now it wants us to verify that this integral is between 0 and 1. Yes. Because cosine is an even function, yes.
So you wouldn't be able to do negative, like out of the...
Cosine of the cube root of x is an even function. Oops, forgot to write dx. So what I'm going to do is I'm going to break that integral into two chunks. Why did I choose to break it at positive 2? What is that integral going to equal? 0. Why is it 0? It's an odd function integrated from negative a to positive a. Okay, right? That was one of the last properties we saw in the notes. So, well, I just wanted to make it so that the lower and upper were opposites. And since the lower is fixed at -2, but the upper is past +2, like it's, you know, like, I mean, I could do from like, you know, like -3 to 3, and then I'd have to tack on, you know, from -2 to -3, but like that seems so weird to me because like the bounds are all goofied. That seems much more natural place to break that. So we have this. Everybody feel okay here? So, yeah, what I wanted to do was take advantage of grab this property 7 that says if f is an odd function, then the integral from -a to positive a of f of x dx is 0. So that's what I'm trying to use since I have an odd function. So what I did was I broke the integral from -2 to positive 3 into the integral from -2 to positive 2 plus the integral from 2 to 3. And I wanted to do it there because that piece, now I can use that property I just cited to make that 0. Does that feel good? Okay. So now all I need to do is to show that this now is somehow bounded between 0 and 1. Everybody's okay with that? Okay, so the piece that I'm going to use there is, I think it's in this section. Yeah, there we go. I'm going to use property 8, which allows me to, gives me a formula on how to bound an integral with a lower bound and an upper bound. So m is going to be some minimum value and m will be some maximum value, right? So, oops, that's not what I want to do. So I'm going to use that property 8 here. So, oops, forgot my integral symbol. So from 2 to 3, sine is in the second quadrant, right? Sine is always positive in the second quadrant. So I know that sine of the cube root of x is somewhere between 0 and 1 on the interval from 2 to 3, right? Sine, I know, is between -1 and 1 always. But since we're stuck here between 2 and 3, I know that it's really 0 and 1 because we're in the one of the first 2 quadrants up top where sine must be positive. So using property 8 then, I know that lower bound times 3 minus 2 has to be less than or equal to so this is like my little m and that's like my cap m. And then 1 times 3 minus 2, and now I'm done. So I think probably the trickiest piece here was making the observation that since we're integrating from 2 to 3, the inputs for sine must be coming from quadrant 2, meaning that sine has to be between 0 and 1 as opposed to negative 1 to 1. But that's the idea. Does that feel okay, Rita? Yeah. Again, ideally, should have been able to do showing it's odd. That's like a trig pre-calc skill, right? And ideally, being able to do that would be great, getting that far, since it should have been relatively fresh in your head to like, oh, it's an odd function. We just talked about this property for odd functions. Like, what can I do with that? This piece here was the tricky part, I think, is going back and going and retrieving a property from like 3 sections ago to create that upper and lower bound that you needed. But that's the piece. Did that feel okay explanation-wise, everybody? And how we got to there? Okay. What else? Okay, fair enough. Let's cruise through 6.1. In 6.1, we're going to be looking at how to find the area between two curves. So say I have some curve here, f of x, and I have a curve here, down here, g of x, and I want the area between them from A to B. So that's looking at this region S. How can I compute that? Well, if I think about this, the integral of f of x dx is going to equal, that area there, right? Everybody agree? I should say from A to B. And then the integral from A to B of g of x dx should equal that area there, right? Now, I'm going to call this piece A2, and I'm going to call that piece A3. Keep in mind that A2 needs to be negative. Why is that? It's below the x-axis. And I guess I'm going to call this part of the region A4. Everybody's okay there? So that area S then looks like it's A4 plus A2, right? Notice that's the same thing as A4 plus A3 minus negative A2 plus A3. Which is the integral from A to B f of x dx minus the integral from A to B g of x dx. And I know that we can distribute integrals. So I can like factor that integral back out. And that's the general idea. Does it feel okay to everybody on kind of how we worked out to there? But that's our general idea. The area between the two curves is one function minus the other function we integrate. Keep in mind, the order that you do this subtraction matters. The curve that's on top has to be in front, and the curve that's underneath it has to be the subtraction. Beck.
Did you include an A3 for the g of x squared?
Why did I?
Yeah.
Because g of x comes up here. Like if I look at the function, right, I have, if I'm integrating g of x, I have this part, and then I have that part, right? It just got a little messy because of all my drawing. But that's the general idea. Now, can anybody see the hitch yet? So there's one little hitch. We'll get to it later in the section. I want to see if anybody can notice it right now. There's one little catch. Okay, well, let's just sit on it. We'll come to it here in a minute. So here's some theory stuff, blah, 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 blah. But here's really what we got, right? So the area A of the region bounded by the curves f of x and g of x, and the lines, the vertical lines x equals a and x equals b, where f of x and g are continuous, and f of x is greater than or equal to g for all x on the interval ab is that integral that we just wrote down. Now I have the question here, what happens if g of x is equal to 0? That's the line y equals 0, right? That's the function. That's the x-axis, right? So this just simplifies down to, yeah, just the integral of f of x dx, right? As you'd hope. That makes sense, I hope, right? All right, let's do an example. So it says find the area bounded above by, find the area of the region bounded above by y equals e to the x, and bounded below by y equals x, and bounded on the sides by x equals 0 and x equals 1. So our integral is going to go from 0 to 1, and then we're going to be doing what minus what? Feel good so far? Okay, let's integrate. The antiderivative of e to the x is, the antiderivative of x is, and then we're plugging in from 0 to 1. So we just get e minus 3 over 2. And again, you could, if you have a calculator, you can make that a decimal. Not wrong to do that. I'm just always going to approach these things as if it's a no calculator problem, because you have those. And anything that's a no calculator problem is obviously can be done with a calculator, and it's not any harder, but okay. That felt pretty easy, right? No big deal. All right. Here it says find the area of the region enclosed by the parabola x or y equals x squared and y equals 2x minus x squared. So here's our picture. What piece of this is given to us that we needed in the picture? Yeah. Right, like the A and the B. What if that picture wasn't given to you? What if it just said it was enclosed by this parabola and we told you the top and the bottom? How would you find those bounds? Yes. And how would you do that algebraically? You take one function and you set it equal to the other, right? Just like you're solving a system, if you want to find the intersection of like y equals yada yada and y equals yada yada, you just set them equal to each other and solve for x. Everybody's okay? So we'll add the x squared to both sides and subtract 2x from both sides to make it equal to 0. Can divide both sides by 2. And then to solve this, maybe we just factor and we get 0 and 1. As we'd hoped, right? Not too bad. Algebraically, right? But if you're not given the picture and you don't know the A and the B, that's how we find them. You set the two functions equal to each other and you solve for x. And now, again, even if pretend we didn't have the picture, how can I tell which function is on top and which one's on bottom? Right? I can tell the first one's a parabola opening up. I can tell the second one's a parabola opening down. Is there any way that this one could be on top of that one if they're intersecting? No, right? So I know that this has to be the top and this has to be the bottom. Again, that's reinforced by the picture, but are you okay with how I just reasoned that through in my head? Again, if it's a no calculator problem, you're not given a picture, those are things you have to ascertain. What's another way you could check? Just pick a value between 0 and 1 and plug it in to both functions and see which one's bigger. Right? Because the only way they can change from top to bottom is at an intersection. Everybody agree? So you pick something in between the two intersections, whichever one, plug that number in, whichever function gives you the bigger value is the top and the smaller value is the bottom. You could do it that way also. And if they're two, like, you have an exponential function, a linear function or something, maybe it's not as clear what's going to be top and bottom. Okay, so we have 2x minus x squared minus x squared dx. So we'll just do some combining of like terms real quick. And I'm going to pull that 2 out front. And now I'm going to do my antiderivatives. Antiderivative of x is? Antiderivative of x squared is? Okay, and then we go from 0 to 1. So I'm going to have 1 squared minus 1 cubed. Well, I should say 2 times 1 cubed over 3 minus 0 minus 0. Plus 0, whatever. So I get 1/3, right? 1 minus 2/3. Does that feel okay there? Okay. And again, if you have a calculator for this problem, you don't necessarily have to do any of this part by hand, right? You can just figure out your bounds by graphing it and finding intersections, right? And on a test, you know, like certainly like you could do this and then just use your calculator to get the rest of these, right? If it's a calculator option problem, just do the setup and use your calculator to finish it off. You know what I'm saying? It says find the approximate area of the region bounded by the curves given below. So what do you notice we're not given in this problem that we had been given before? The intersections, right? The bounds for our integral. So how do we find those? Set them equal to each other. I think this one's going to be kind of stinky. What do you think? Yeah, you'd have to like square both sides. I foiled that to get there. And then you'd have to multiply both sides by x squared plus 1. And you'd have to FOIL that piece out. Yuckarooskies. And then you'd have to subtract that other x squared over. And now this algebra is getting too bad for me to do by hand, right? So calculator would be okay. So from the picture, hopefully nobody's surprised that x equals 0 is an option there. You could settle it right away, because if you plug 0 in, you get 0 over not 0 equals 0 minus 0. Is good enough. That's a solution. And the other one is about 1.38. I'll read this. Oh no. That's a 1/8. All right. So, integral 0 to 1.18 of x minus square root of x squared plus 1 minus x to the fourth minus x dx. And yes, to solve that, I graphed it, found the intersection. Probably from the get-go. Because looking at that, like, yuck, already didn't look like one that was going to be fun to do algebraically. And it turns out as we get into it, it's going to be not realistic to do algebraically. In fact, I think that's, well, 1.18 certainly appears to be an irrational solution. So solving a polynomial and finding an irrational solution where there's only one irrational solution by hand, I don't know is going to be realistic for anybody. Certainly not me. So there's that. And what are we going to do here to integrate this thing? Well, I would want to do something first. I'm going to distribute my integral because substitution, certainly I need to do that for that first chunk. But this other chunk, I can handle no problem without it, right? So hi, Renzo. Morning. So for that first piece, our choice for u should be x squared plus 1. Then we get that du over 2 is going to be x dx. And then I'm going to redo the bounds. Is everybody okay with that? Katie? So I would have just y1, y2, and then graphed and found the intersection. Yeah. So there should be one at 0, and there should be one out like that 1.18. Back.
What's the benefit of redoing the bounds?
What it's going to allow me to do is after I do my antiderivative, I can plug it directly into the u as opposed to having to put the x back in and then use the original bounds. But you can do that if you'd like. It's not wrong to do that. It will work. It'll be fine. And there's not tons of benefit, particularly on a problem where you're assumed to have your calculator anyways.
I just didn't understand.
Right. Yeah. No problem. Okay. So what do we have now? So this is the integral from 1 to 2.39 of 1, well, let's write it as u to the negative 1/2. And then I'll put the 1/2 in front and just a regular old du. And the other one we're not touching. That's going to just stay the same for us. Now I'll do my antiderivatives. And again, at this point, if you have a calculator here, like I'm just typing this stuff into my calculator and having it do the integral to find the number for me once I have it set up. If it's a calculator option problem, like once you're here, dude, I'm just typing that into my calculator and pressing enter. To get the number, I'm not actually plugging stuff in. You know what I'm saying, guys? So what I did is I took the 1.18 and I plugged it into u. So 1.18 squared plus 1 is 2.39. The advantage there is that I don't have to plug the u back in. Oops, goodness gracious, Mr. Kulik. That's not right. There we go. Okay. Has anybody seen the hitch yet or thought about the hitch yet that I tried to prompt you to think about here earlier? Okay. I'm going to just tell you then. What if the top and bottom curve changes over the course of the interval? Well, if we're going from A to B, what if the curve that was on top ends up on bottom at some point and then back on top again? Yeah, you're going to break that into 3 separate integrals. So you need to find whatever that C is and whatever that D is. So you do like A to C of f of x minus g of x dx plus the integral from C to D of g of x minus f of x dx plus d to b of back to f of x minus g of x dx. Is everybody okay with that? Now, symbolically, what is this equivalent to? Because if I leave it the way it is, just S2 would be a negative area, right? So if I just do the absolute value of the whole thing. Now, to do this in practice, what do we have to do? I have to do that. So, like, putting the absolute value in there, woo, big deal, Mr. Kulik, just saves you some writing. It's like elegant way of writing that integral rather than having to arbitrarily many chunks because we don't know how many times it's going to switch from top to bottom. So usually we just write it as an absolute value, but in practice, that's what you're doing. Does that make sense to you guys? So it's the same way we have attacked the integral of absolute values in the past, right? Okay, and there's the formula. So let's do an example here. So we want to find the area of the region bounded by the curves y equals sine x and y equals cosine x on the interval from 0 to pi over 2. So we have a picture here. We can see that the intersection of the two curves is at pi over 4. Should you know that without a calculator? Yes. How do you know that? On the unit circle, pi over 4, sine of pi over 4 is root 2 over 2. And cosine of pi over 4 is root 2 over 2. They're equal, right? Everybody's okay with that? Now, honestly, you could do this algebraically as well, if you didn't remember that. How do you solve this equation? Yeah, so you divide both sides by cosine. And remember that that is the same thing as tangent. So you're doing tan inverse of 1, which is pi over 4. But, I guess it doesn't matter. It is worth checking to make sure that's not an extraneous solution. But clearly cosine of pi over 4 is or isn't 0. All right. So we're going the integral from 0 to pi over 2 of the absolute value of cosine x minus sine x dx. And that's going to be the integral from 0 to pi over 4 cosine x minus sine x dx plus the integral from pi over 4 to pi over 2, and then switched sine x minus cosine x dx. So far, so good. What's the antiderivative of cosine x? Right? Antiderivative of cosine x. Nope, the derivative of cosine is negative x. Or negative, yeah. This is just positive. And then what's the antiderivative of negative sine x? Cosine x. Okay. And we'll go over here. The antiderivative of positive sine x is the antiderivative of positive sine x is negative cosine x. If you know it, just like shout it out. Take a risk. It's okay. And the antiderivative of negative cosine x is negative sine x. Oops, that was supposed to be pi over 4. I forgot the over 4. So far, so good. Oops, that's not what I wanted to do. Yuck. All right, fine, whatever is being difficult for me. All right, so we have root 2 over 2 plus root 2 over 2 plus or minus 0 minus 1 plus negative root 2 over 2 plus, oops, sorry, that should be pi over 2, so that should be plus, sorry, plus, then negative 0 minus 1 minus a negative root 2 over 2 minus root 2 over 2. So I get 2 root 2 minus 2, I think. Yeah, good. Is everybody okay with what I did to kind of finish up there? Katie? Mm-hmm. So if I look at this part, the function on top is sine, and the function on bottom is cosine. So I had to switch, if I want the area between the two curves, to top minus bottom.
We don't know.
Well, so to find their, so here you're told what to go between, right? If you're not provided a graph, you would need to check to see if there's an intersection in between those two, which is what we did right here. And to figure out which one is on top and which one that's on bottom, I can pick something between 0 and pi over 4 and plug it into sine and cosine and see which one is the bigger number and which is the smallest number. So in that case, pi over 6 would seem to be the notable, if you don't have a calculator, the obvious choice, since that's a unit circle value, right? When we have the unit circle memorized, ideally. So I know that sine of pi over 6 is 1/2, and cosine is root 3 over 2. So cosine would be on top. And then over here, between pi over 4 and 2 pi over, or pi over 2, I'd probably pick pi over 3. And I know that sine of pi over 3 is root 3 over 2, and cosine of pi over 3 is 1/2. So there, sine is on top and cosine is on bottom. Does that make sense on how I would do this with no calculator? You probably wouldn't have to do it with no calculator without a picture. But if you were asked to, that is how I would do it. Does that... Probably they would give you a calculator, or at worst give you the picture without that there, without that value there, where you'd have to find that first. But that's not so bad. Does that feel okay? Okay. What if the functions aren't written with the x as the independent variable? What if I want to find the area between the two curves and they're like going kind of up and down, where the area I'm looking at is between them this way? Well, it's the same idea, just where instead of integrating with respect to x, we're going to integrate with respect to y. So our bounds are going to come from the lower bound on the y-axis and the upper bound on the y-axis. And then instead of doing top minus bottom, we're going to do right minus left. Is that okay there? Okay. So here it wants the area enclosed by the line y equals x minus 1 and the parabola y squared equals 2x plus 6. So if I want to do this with respect to y, I want to write each of these two equations as x equals equations. Write it this way. Is everybody okay with what I did there? Okay. Now, one, I want to find the intersection of these. But I want to find the y coordinates at the intersection, which is convenient because I've written them already as x equals equations. So I would multiply everything through by 2 to get rid of the fraction. Then if I move everything onto one side, oops, minus 8, dum-dum. And then I can factor that to be y minus 4y minus 2. So my solutions there are y equals 2 and 4. Does everybody feel okay in how I found my bounds? Uh-oh. And now I want to figure out which one of them is left or right, correct? So I'm just going to pick a y value between the 2. What's our obvious choice? Yeah, hopefully 3. So we know that this one is the right and that one is the left. Is everybody okay with how I determined that? I just was looking for which x was bigger, right? Because that's going to be further to the right. So now I have everything I need to set this up. Integrating from 2 to 4 of the right-hand function minus the left-hand function with respect to y. And let's do a little cleanup there before. So far, so good. All right. Let's do our antiderivative. So what's the antiderivative of negative y squared over 2? Over 2 times 3, right? Or if you want, we could do that. Maybe that way is a little clearer as to what we did, right? Oh my goodness gracious, guys. Look at what I look at this. Did I factor that right? No, what should it be? Yeah, it should be plus 2. So that should be minus, that should be minus, that should be minus, that should be minus. But everything else is still okay. Glad I caught it at that point. It's like, that doesn't seem right. Like I'm looking at what the answer is supposed to be in the book and I'm like, oh, that's not going to get me there. All right, so we're going to have negative 4 squared over 6 plus, 4 cubed. And then 4 squared over 2 plus 4 times 4 minus negative 2 cubed over 6 plus negative 2 squared over 2 plus 4 times negative 2. And that should come out to be 18. Does that feel okay, Rita?
How do you know if it's like an up minus down or the right minus?
Sure. So if we tried to construct, well, one dead giveaway is that it's not set as a y equals, right?
Oh, it is.
Because it's y squared. So it's like x is not necessarily the independent variable here. But if we looked at the graph of this, squared equals 2x plus 6. You have that. And if we think about the graph of this, if I try to do it this way, this curve is top and bottom for a portion of it, and that makes life really kind of tricky to try to do it in terms of x. It's possible. You'd have to break the integral into like an up-down integral from -1 to, 4 or whatever, or 5, where they intersect. And then you'd have to figure out the integral here, which isn't bad. You could do -3 to -1 and then multiply it by 2 because we see it's symmetric on top and bottom. But if this wasn't symmetric, boy, howdy, that's going to be a royal pain in the duty. So like this one's still recoverable, but again, they would probably give you a picture to go along with this to give you the hint that like, hey, you need to do this in terms of y instead of in terms of x. But your dead giveaway is that you have like a function of y here, right? Like it's not just a y by itself, it's like y squared or y to the third or square root of y or sine y or something, rather than just y, because now getting the y by itself, you have to introduce a plus or minus to square root both sides, and like, what do I do with that if I'm trying to integrate? Like, is that on top or bottom? Yeah, it just becomes like kind of a problem, right? Okay. So I'm not going to assign anything for a homework quiz from this section because, quite frankly, next time we're going to do the homework quiz is going to be based on some of the free response or multiple choice questions for the tests that I've put in. And we'll do some more practice with those guys next time. We still got 10 minutes. Do you want to run through one of these here real quick? No homework quiz on 6-1.
Oh, like it's like the homework quiz for next class is on the
Yeah.
Oh.
Yeah. Katie.
This Friday?
Yeah. All review. We're just going to do like MCQ and FRQ stuff. Lorenzo.
Are you supposed to keep the MCQs?
I will. After we've done Friday, or after Friday. Is that okay? I got a key. It's pretty good, I think. There's probably still mistakes because that's what I do. All right. So let's take a look at this one. So this says the continuous function f is defined on the interval from -5 to 8. The graph of f, which consists of 4 line segments, is shown in the figure above. Let g be the function given by g of x equals 2x plus the integral from -2 to x of f of t dt. Find g of 0 and find g of -5. Well, that much is probably pretty straightforward, right? How am I going to find the integral from -2 to 0 for f of t dt? I'm just going to use the graph, guys. Right? Isn't it just this area? What geometric figure is that? It's a trapezoid, right? So there's like base 1, base 2, height. The area for a trapezoid, 1/2 base 1 plus base 2 times height. Everybody's okay there? You could chunk that into like a rectangle and triangle if you wanted. That's fine also, right? If I want g of -5, well, that's going to be 2 times -5 plus the integral from -2 to -5 f of t dt. Well, what do you notice about that integral? That's goofy. The bounds, right? So let's flip those. Oops. And what do we need to do to flip the bounds? We have to make the integral negative. So now we're looking for the area between -2 and 0. So that's two triangles, right? So the first triangle is 1/2 base, which is 2 units on the x-axis, and -4 units down the y. That's going to give me the negative area because it's under the curve, right? Or under the x-axis. Then plus 1/2 the area of the other triangle, whose base is 1 and whose height is 2. So that's going to be -10 minus -4 plus 1. So that's going to be -10 plus 3, or -7. I think. Is everybody okay with that? Yes, Katie. Nope. 1/2 base 1 plus base 2 times height. Or you can just chunk it into a rectangle and triangles. Like, it's okay to just, like, divide it up. For something like this, it's real gritty. You could just do something like that and make it a rectangle and a triangle, and you don't have to do the trapezoid. Is that okay? And again, that's if you don't remember that formula, like, that's what I would do. I'm just going to keep it simple. I know rectangles, I know triangles. Let's keep it at that. Part B says find G prime in terms of f of x, and then it asks for G double prime of 4 and G double prime of 2. State the value or explain why it doesn't exist. Okay? So G prime is going to be the derivative of this, right? That's it. Everybody agree? So the second derivative is going to be the first derivative of f. So if I want G double prime of 4, that's the derivative, first derivative of f at 4. How do I do that? So let's see, 4 is like here. What am I going to be doing? Slope, so slope. Yeah. So like -3 minus 3 over 8 minus 2. Whatever that is. And then G double prime of, what was the other one? -2. Equals f of -2, which is, what's that going to be? What's the slope at that point? Tessa, what'd you say? Nope, not 0. Okay. Great. So you'd say it does not exist, or undefined is fine. And the reason is it's a sharp corner. Notice I was specific. I didn't use any personal pronouns. No it's. I stated clearly what it was. That would be f. Part C says, on what intervals, if any, is the graph of G concave down? Give reason for your answer. I think this is probably the trickiest piece. Concave down is where the second derivative is negative. And remember, the second derivative is the same as the first derivative of f. So where's the first derivative of f negative? On those intervals. Why? Negative slope. Yep. Is that all I need to do? Yeah, Mr. Kulik, that's it. So negative 2 to 0 and then 2 to 8. Again, not difficult to do, but like you have to understand what you're looking at, right? And now, again, like I've done these problems in advance, so that's one advantage. And two, like, you know, I'm Mr. Kulik and not doing this for the first time, which is another huge advantage. The next one says h is given by h of x equals g of x cubed plus 1. Find h prime of 1. So h prime is going to be 6x squared plus f of x cubed plus 1 times 3x squared. Yes, Katie?
Sorry, when you like have these things like the first triangle for like g and negative 5, like the half 2 times negative 4. Why is it like negative?
Well, so that's this area, and since it's below the x-axis, it needs to be negative. So I just always just use the negative y value, and that just reminds me to, you know, yeah. And if I go to my graph, then f of 2 was some number, 3. So I get 15 or something there. Again, try to take some time tonight, work through some of the MCQs and FRQs. After Friday. Yes. I have them all ready to go, but I want to give you guys a chance to try to do stuff without having me tell you the answers first, which I know is rough, but I think it's good practice.
On the test, are we